I'm Alexander, this is Amit. We're both graduate students in the Princeton NLP group, and we very much work on related topics to what we're presenting today, and yeah, it's very exciting. So the basic outline of the talk is, I'm going to talk in the first bit about how to build a large language model from scratch. I'm not going to assume much prior knowledge in terms of the technology that goes into it. And these large language models are really the kind of foundation of ChatGPT. And without these large language models, ChatGPT wouldn't be possible. And then Amit in the second act will talk about what ChatGPT, how it sort of builds upon these large language models, and what kind of capabilities we get. Oh, not sure why the screen just died. Okay, excellent. And about the kind of capabilities that we get from ChatGPT and also some of the pitfalls. So the fundamental question is, how do we represent natural language in machines? That's also the fundamental problem in sort of natural language processing. And if you've done any sort of coding, I think you're very familiar with strings, which is how we usually represent text in programming code. And here, every character is encoded in a byte or 2 bytes. And these things are great if we want to represent, if we want to store text, or also if we want to manipulate text and maybe sort of put different bits of text together, or like do some kind of search and replace. But just representing each character individually gives very little sense of what the meaning of words are, or how we sort of any kind of higher level operations we can perform on the text. So in NLP, we usually represent words individually as numbers. So we call this tokenization. We map each individual word to a number, and these numbers will go from maybe like 1 to like hundreds of thousands of numbers. And in practice, there are some pitfalls because there's a really large space of words, and also words can be misspelled. You can create new words. It's a very sort of unbounded space. So instead, we found this medium where we do subword tokenization. So we kind of find common bits of words and then represent text. This is an example here. The text will be Python encodes text as Unicode, and these would be all the Unicode bytes for each individual character. But instead, in NLP and also in ChatGPT later on, we use a tokenizer which breaks the text down into these bits, which occur fairly frequently in text. So Python is captured as one word, but actually encodes is already another word that we split it up into n, and then these special token means that this isn't the start of a word, but the middle bit of a word. So encodes and then text as Unicode. And these will be the corresponding IDs. And then once we move to machine learning models, these will be the inputs to our models. So this is kind of a good compromise between sort of operating already on like a higher level plane where words are kind of linked to something that actually is like a unit of meaning in a text. It's not ideal, it's very heuristic, but it works very well in practice. And this way, every text can be represented as a sequence of tokens. Yeah, Devin?
These IDs, how do those actually get passed into the model? Like a one-hot encoding or something?
Yes, it will be a one-hot encoding, but we'll come to that in a second. So Devin's question is really good. How do models actually make use of these IDs? By the way, feel free to ask questions at any point if you're interested in anything or stuck on something. What we usually do, because these individual IDs are still sort of very disparate and don't give any sense of how similar words are. So we would actually like to operate in a space where similar words can sort of have a similar representation. And for this, we use word embeddings. Word embeddings are huge vectors. So usually they're like thousands of dimensions. So like a vector in 2 dimension would just be kind of like a point on a 2D plane, and in 3D it would be like maybe a point in this room or something. But we use like 100-dimensional to, actually ChatGPT probably uses like 1,000-dimensional vectors. And this is really great because if every word is a point in the space, so this is a projection of one of these vector spaces down to 3 dimensions so that we can kind of visualize it, but it's actually much, much higher dimensional. And it gives us the ability to learn a representation where similar words will map to similar vectors. So here in this representation, I kind of select different words at different times, and it always shows words that are nearby. And like something that might occur is if like Princeton comes up, like university will be nearby, and other universities, also similar universities, should get assigned a similar vector. And something really powerful about this as well, because we have so many dimensions, which gives us also so many sort of directions of freedom. So if there is a specific axis of similarity, these models have like thousands of these axes. So they can sort of simultaneously learn to map Princeton close to New Jersey, but also close to Yale and Harvard. But then like Yale and Harvard will not necessarily be mapped closely to New Jersey. And this really is only possible in very high dimensional spaces. Any questions? So this is like a key concept that really powers a lot of machine learning models for language. And we have to learn these vectors. So we learn these vectors from text. And it just so happens if we have, if we sort of predict words from one another, that we actually end up with representations that have these desirable characteristics. So the basic formulation of a large language model is very simple. We want to assign a probability to any sequence of text. And any sequence of text means any sequence of tokens, once we've tokenized it. So some intuitions for what this might mean. We may want to say that the probability of dog as like a human utterance should be more likely than a probability of turtle. That just by virtue of the fact that we usually talk more about dogs, it's like a more sort of overrepresented concept in like most bodies of texts, so that should be higher. If we have a text, a turtle swims in the ocean though, even though turtle occurs less often than dog, we may actually want to assign a higher probability to that than the text, a dog swims in the ocean, because that's sort of a more natural concept. And this is exactly the kind of, these probabilities actually come from GPT-3, which is sort of the precursor to ChatGPT. So GPT-3 has learned that a dog swims in the ocean is sort of a less likely thing than a turtle swims in the ocean. And the probabilities here come from the actual just occurrence of these words on the internet. So a dog occurs about 100 times more often on the internet than turtle. And when we model these things, we actually just split it up into individual parts and then use the chain rule to break it as like a chain of probabilities. So a turtle swims in the sea would be, in the ocean would be the probability of just and then a turtle given A, and then swims given a turtle, and then in given a turtle swims, and we just break it up like this. And what these large language models will do is just assign an individual probability to all these individual components. That's what we want to learn. And that gives us a lot of power and flexibility. And really, I think a keystone in like powering this probability is the transformer architecture. How many here are familiar with the transformer architecture? Cool, that's great. So this is a neural network model that is easy to optimize, can be scaled to really large lengths, and sort of enabled really the rate of progress that we've seen in NLP, and that has led to ChatGPT. It's a very simple design. And actually, just to start off with, like a way you can think about a transformer is just, it's kind of like a computer that instead of doing sort of hard logic, operates soft logical executions. And then we can sort of efficiently compute these programs. But we can also, because they're sort of soft, we can also then go back and optimize them for like a specific kind of data set that we see. So they're a little bit like sort of differentiable computers. And they're built out of blocks. We stack a lot of decoder blocks on top of each other, and each decoder block consists of two components, self-attention and a feed-forward block. So I'm going to talk about each of these in a little bit of detail. But the input to this model, so we input a text, again, a series of tokens, and we just predict the next token. That's the basic premise. And the input here is exactly these kinds of vectors which we've seen previously. So we learn these kinds of embeddings, these very high-dimensional numbers, and these will be the input bits to our model. And essentially, we just have a big table for everything that we've tokenized for all of these little words and subwords. We just know what their embedding is, and whenever they occur, we input this high-dimensional vector into our model. So self-attention is the first operation that occurs in these blocks. And the purpose of self-attention is, I think, is to move information from previous things that have occurred in the context to the current prediction. So essentially, each of these vectors, as we go to through the model, we operate in this vector space, and we map one vector to another vector. And the self-attention bit allows us to learn where to look in all these previous tokens that have occurred, a little bit almost like a lookup operation, and then take whatever vectors we've had there, move them to our current prediction, and integrate that knowledge there. And because we stack these layers, we can do this over and over again. So like you can implement sort of copy operations with this. You can implement like a lookup, whether something has occurred previously in the context. And that way we can almost learn a function which looks at all the words that have occurred previously and predict what should be next. I should also say, in practice, we have this detail where what we call masked self-attention or causal self-attention, where a certain token can only ever look at all the tokens that occur to its left. The reason is, if we want to predict the next token, if we could see into the future, that would be very trivial. We just copy the token from the future, and we would never learn any sort of interesting prediction. So at each position, as we encode, for example, robot here, we can only look at A. And if we encode obey, we can only look at what's to the left of it. Any questions? And the kind of specific shape that this prediction takes is that for each of these tokens in our input, we create keys, queries, and values. And these are all just new embeddings that we create from the previous embeddings. And then we essentially select, with the query embedding here, we select the key embedding that matches it most closely, and then use the values of the value embeddings at these positions to produce the output of our attention layer. But it's sort of inspired by like a simple database lookup, but with these like soft embeddings. Yes?
How long does it go back, this lookup?
So usually we operate on sequences. So GPT, like ChatGPT, has a context size of 4,000 tokens, which is quite significant. It means, I mean, it's sort of a good few paragraphs of words, around like 3,050, 500 words on average. And the last token will be able to go to any previous position. So it actually will see a lot of context, which also means the model really has to learn embeddings which sort of align very well, because there is a lot of information that you could pick up from the context.
Why 4,000 tokens and not 10,000 or
Yeah.
500? Is there a difference in quality, or what does it change?
So the context window size gives you like the maximum amount of parsed information I can sort of aggregate in my current token. So if it was just 500, like after like 1,000 tokens, the model wouldn't know anymore what happened 500 tokens ago. So you would want to have it as large as possible to see really long-range dependencies in text. But there is a computational constraint, because if you have to, given you have to aggregate over this entire sequence, at some point it becomes very inefficient for every token to give it, for the last token to look at like 10,000 previous sort of positions. It's probable that because these models become larger and larger, like 2 years ago it was just like 500 tokens. Probably in like a year or 2 years it will be 10,000 tokens, but yeah, this context window will remain like a fundamental sort of limitation.
The limitation is to the computational.
Yeah, it's the computational efficiency, yeah. Cool. Then the second type of layer is a feed-forward layer. And now in each of these positions, so previously we've integrated information between tokens. Now we look at kind of a memory that we've sort of cached in our model, that we've learned from the text, and again map one embedding to a new embedding. So the idea is that maybe if in your text you've always seen embeddings like it will take a, or every once in a, and a for a, via your attention layers, you want to map all of these previous tokens to a similar space in the embedding. And then using these feed-forward layers, which are really big, this is also where like the most amount of parameters are in the model, you learn some kind of mapping that all of these embeddings will be mapped to the embedding for while. Because you want to predict at the end of the model that while has a high likelihood of following all of these concepts. And it's in these feed-forward layers where also a lot of like factual knowledge is stored. So if your text if you see the text, the Barack Obama is the president of the, and you have to know that the kind of most likely continuation will be United States or the USA or the US. You want to learn a similar embedding for all of these concepts, for USA, US, America, and so on. Or this is what the model will try to achieve. But it also just has to learn a mapping between essentially some concept for president and Obama to the US. And so aggregating that information from these other tokens will occur in attention, and then mapping president of the US, Obama, to president of the US will occur in the feed-forward layers. So these, again, are kind of key value stores, but now with some kind of fixed cache that we try to learn. So, and then at the end, we do this for a lot of layers. So in GPT-3, which is most likely, we don't totally know, the sort of underlying model of ChatGPT, it's about 100 layers. So that gives the model a lot of flexibility to move things around its sort of memory and then map it from one token to another. And at the end, we get another embedding. So we put in an embedding, we transform it using the evidence from all the other token and what we stored in the memory. We get a new embedding. We just compare it with all the embeddings which we have in our table. So all the embeddings for all the tokens that we have. And that gives us a bunch of scores. So over the entire vocabulary, all these tokens, which will correspond to like a wide variety of concepts and sort of sequences of characters, we get a score. And then using a very simple operation, we can just convert this score to a probability distribution. And then from that probability distribution, we try to match it, or like we can take the word which is most likely or occurs with a certain probability. So the next question becomes, how do we actually train this? So if I take one of these transformer architectures, I usually just initialize it with a bunch of random embeddings and random operations from one vector space to the other, and it will not model language. It will just produce random noise. But because everything is a soft operation, we can optimize it using gradient descent. And so we learn all these weights and all these transformations from data. So the basic procedure is that we have an expression for what the probability of the next token is given previous tokens. We know what actually occurs in real data because we just sample, we just take sequences of text and of tokens from the internet or from books or from wherever. We're going to talk about it in a second. And we can just check what actually happened next. That just gives us one instance of what could have occurred next. But the idea is if we do this for enough text, we learn a good probability distribution over what actually happens. So we check the probability distribution of what actually comes next. So the president, Barack Obama is the president of the US, so US would be the next token, and we just try to maximize that probability. And the way we do that is we have all these parameters in our models which determine these, for example, these embeddings in the input layer. In the attention layer, we learn an operation to look up previous tokens. In the feed-forward layers, we have these transformation from one embedding space to another. And we can compute the gradient to each of these parameters. So that means we just sort of keep track how each individual parameter affects this probability. And then we try to just change each parameter a tiny bit by increasing this probability. And given in these big models, there are billions of parameters, that seems not that kind of, it seems kind of magical that this can happen, given like we can change the value of 1 billion parameters to make this probability more likely. But we also, as we do this optimization, we average the contribution of these parameters over lots and lots and lots of predictions, so like millions of predictions. And then we will get essentially, every parameter will try to increase the average sort of likelihood of the text that comes next. And individual parameters will move in the sort of direction that makes the biggest impact. And to some extent, they will specialize on specific sort of specific subsets of the text and specific concepts. And then we also repeat this over and over again, millions of times, to really have a good fit of this function. Yeah?
A little bit more concretely, like what does one of these batches look like? Like say I have 3,000 tokens, is it like the first piece of the batch is the first token, and then the next is like you give it 2 tokens, and the next is you give it 3? So on.
Yes, so we can get like thousands of sequences, just random sequences from the internet of words, and then for each sequence we can also at each position make a prediction. So we can predict the second word from the first word and the last word from all the previous words. And
also say you have like a document that's like 10,000 long and your context length is 4,000, right? Do you split that up like 4,000, 4,000, 2,000, or you're just like randomly sampling small chunks from it?
yeah, you just you would typically split it up. You would try to sample in a way that your document always starts at the first position that your transformer sees, but then if the document is too long, you just move it into like a new sequence. Any other questions? Yes.
Just confirm, are you referring to batch gradient descent right now?
So yeah, in practice we do like mini batch stochastic gradient descent. We can't use these transformer architectures are not easily optimizable by standard gradient descent. So we use some adaptive gradient descent algorithms. So Adam is typically used. Yeah.
I guess the other thing is, do we know anything about whether, like, in the training process, if there's been any experimentation, sort of like shuffling the input order, or basically like this, like introducing randomization at that stage?
Shuffling the tokens in.
The order of the samples
Yeah.
and what's in each batch,
Yeah.
like, are similar documents in each batch.
So it's very robust. if we just change the kind of random order of sequences that we see, or we change the initialization point of the model, because there are so many parameters, it almost always just converges to a good solution. Not always the same solution, but the sort of variance between solutions is very small. Yes?
Can you just clarify, when you say parameters, do you mean the position of a certain token in certain dimension of this 1000-dimensional embedding?
Yep.
Or do you mean something else?
Yeah, great question. So actually, the parameters of the model come from a bunch of places. So it comes from these 1000-dimensional vectors, but then in each of these layers I've described, these transformations are also learnable in the sense that they're parameterized by like weight matrices. And these weight matrices also contribute to the parameter count. So in the feed-forward layers, for example, it's like a 2-layer neural network where we have weight matrices that first map it to a very high dimensional space and then map it again to like a lower dimensional space. And these contribute to the parameters. Yes?
So basically, there is no really any kind of mathematical framework. You just try whatever works.
In some sense, that's correct. It does, I would say, it is like this architecture is the accumulation of like a lot of experimentation, and there are various sort of small details.
But I know that there was a lot of work on semantic representation, in the 80s and 90s, and they were quite successful. So, but they cannot be, in a sense, integrated with this approach. Are they, in principle, incompatible, or if there is a route to do it?
I think that's still an area of research. I would say these things produce very capable semantic representations learned purely from data. And because they are so effective at scale, it's actually the thing that a lot of NLP researchers have been struggling with is that sort of previously successful hard-coded semantic representations don't actually give any additional value from what. But yes, there's no mathematical framework. I think the machine learning community has worked out a number of analysis techniques and also sort of more mathematically motivated techniques to show that a lot of the architectural decisions that we make in this architecture and in the gradient descent are well motivated. But there is nothing super hard that gives a guarantee that this should work. Yes?
What's the role of like human like reinforcement learning in this? Like, isn't there like a process where like, for example, I know OpenAI has like human labor, and like basically you like create text and sort of decide like what the text is better, and that's what you want to model. What's like the role of having optimizing as well?
So far, none. So this foundational model, where we just learn a model of sort of language data, features no reinforcement learning. But you're totally correct, it is a part of ChatGPT, so Amit will talk about that in the second part. Cool. Okay. Yeah, so also to, again, illuminate the scale at which these things work, we use very big data sets from the internet on which we train these things. And the kind of vast scale of data is really important to achieve high quality models. As like an analogy, the kind of amount of data that ChatGPT sees would be equivalent to reading continuously day and night at like top human speed, top human reading speed from like the times of ancient Egypt. So it sees vastly more data than a human could process in an entire lifetime. And a typical data set would consist of lots of different domains. There is a lot of sort of handcrafting here and manual engineering to procure high quality data and scrape it from the internet. So I think popular sources will be archive. These models see archive papers. These models see data that's just scraped from the web, so just sort of web crawlers. They see Stack Exchange answers, so like programming help. Wikipedia, they see Wikipedia often in multiple languages. They see online sort of libraries like Project Gutenberg and so on. They see YouTube subtitles. They see GitHub. They're just simply trained on code as well. That actually turns out to be very helpful for a lot of the capabilities to just learn how to model code as well. They see legal texts. They see like medical articles. It's really like very large scale. And then briefly at the end, once we've trained these models and we've actually learned a good function that approximates this probability of what comes next, given what comes previously, we can just plug it in and sort of bootstrap off the predictions. So we put in, this is what we call conditional generation. We put in a prefix, look what the model predicts next, take one of the guesses of the model, put it back into the input, look what comes next, put it back into the input. And this way we can sort of generate long sequences of texts. Yes?
Does each additional token in the output sequence require an entire forward pass of the model?
Yeah, great question. So because we have this self-attention where things, it can only look back, we can just cache whatever happened in the past because we also don't have to train it. That way we just can take this embedding, sort of process it locally, use the cached values, and then, yeah. And so that it's efficient in practice. Yes?
In the previous slide, how representative is this distribution of the data that ChatGPT?
Yeah. So one annoying thing about OpenAI is there is very little detail on, at this point it's a proprietary technology and not an open research contribution. So we don't know what exactly they do with the data. And there does seem to be also some special engineering involved that is not public because open source sort of effort to create similar models using data sets like the pile often just are less good in practice than like the OpenAI models. Yeah, and then really the key is we scale up in every direction. We make the models wider, deeper, they take more parameters. So this is actually a very outdated chart from 2020 where the largest model was just 1.7 billion parameters. Nowadays, GPT-3, again the likely model for ChatGPT as well, has 175 billion parameters. The largest models, like Google's Palm, have 500 billion parameters. And they're also trained on like billions and billions of tokens. So even the data set I showed previously is small compared to what Google would use. As like a little sort of helpful sort of guidance to really use these models in practice, and also if you don't just want to use like a sort of online interface to interact with the model, Hugging Face is a great resource for downloading smaller models and running them on GPUs or CPUs. And you can just download these models from the internet. You can look at all the weights. You can look at every single layer and every embedding. You can generate predictions. So it really is like wonderfully convenient if you know a bit of Python as well. So I can, for example, just put some input. I can tokenize it first. I load these pre-trained models, I tokenize it, I run it through the model, and then I generate some predictions, or I can also just generate some continuous text. So here the input was the capital of the US's, and this is a much smaller model, just like 125 million parameters. And it predicts Washington correctly, but then if you keep generating it, it will also predict DC, and then continue, it will kind of think this is the format of the text and will continue generating similar tokens like it.